Hello everyone, my name is Senwei Liang from Purdue University. Today my topic is solving PDEs on unknown manifolds with machine learning. This is joint work with Professor Si Xiaojiang from Shanghai Tech University and Professor John Harlin from Penn State University and Professor Haizhao Yang from Purdue University. Solving PDEs on unknown manifolds embedded in high-dimensional MPs is a challenging computational problem that commands a wide variety of applications. For example, in physics and biology, such problems arise in modeling the granular flows, liquid crystal, and biomembranes. Also, in computer graphics, PDEs on surface has been used to restore the damage patterns on the surface and brain imaging. Many methods has proposed for solving the PDE on surface, but most of them are limited to solving the PDE on surface of not very high dimension, for example, only in dimension R3. They typically parameterize the unknown manifold and use the tangential derivative to solve the PDE. For example, the finite element method that represent the surface using the triangular meshes. And some method will estimate the embedding function of the surface, such as level Z representation or the closest point representation. Also, some method will use the weighted-based method to solve the PDE on unknown manifold. The key issue with this approach is that when solving the PDE on the surface of high-dimensional ambient space, the computational cost may not be feasible. Also, it has been pointed out in some papers that some approaches may not be robust, and also the convergence near the boundary can be problematic. Now, let me introduce a diffusion mapping-based PDE solver on unknown manifolds. The unsupervised learning method called the diffusion mapping algorithm was proposed to directly solve the second-order elliptic PDE on the point count data. They approximate the differential operator with local kernel integral. The main advantage of diffusion mapping-based solver is that it avoids the tedious parameterization of submanifolds in the high-dimensional space. However, the estimate solution is represented by the discrete vector. Similar to the finite difference method, we can only get the solution on the given points. However, if we want to load the estimate solution on the new points other than the given data point count, we use some interpolation method to estimate the solution from the from the solution we obtained already. However, if the unknown manifold is very complicated, it's not easy to do the interpolation on the new points. Also, another problem of the diffusion mapping is that the size of the metric approximating the differential operator increases as a function of data size. So it means it will create a computational bottleneck if the PDE solution involves the inversion of the eigen decomposition. And when I introduce the diffusion mapping officially later, we will see this problem again. One possible way to mitigate this limitation of diffusion mapping is the use of neural networks. In recent years, we have witnessed the success of application of neural network in scientific computing. It has been pointed out in many papers that diffusion mapping have good approximation properties, and it can lessen the curse of dimensionality. Also, there have been wide application of neural network in high-dimensional PDE on the Euclidean domain. They typically will formulate the PDE problem as a regression problem, and the PDE solution is parameterized by the neutral network. And lastly, with the development of computation tools like the TensorFlow or PyTorch, and also the built-in optimization algorithm like stochastic gradient descent or ADAM, when it is more simple than the conventional method that to develop the mathematical software with parallel computing using the neutral networks. In this talk, I will introduce our method to solve the PDEs on a non-manifold by incorporating the diffusion mapping algorithm in the neutral network-based PDE solver. Firstly, the diffusion mapping algorithm is employed to approximate the second-order elliptic differential operator defined on the manifold. And then least square regression problem is formulated to imposing an algebraic equation. And then we will solve the resulting empirical loss function by finding the solution parameterized by the neutral network and using the optimization algorithm like SGD and ADAM. Now we come to our problem setup. We consider manifold M is a d-dimensional bounded and closed submanifold, and let U is the function on the manifold and is also a solution of elliptic PDE. And the formulation of elliptic PDE is in equation 1. And here we use the notation L to denote the differential operator of this term. Here we use the subscript G for the operator defined with respect to the Riemannian matrix G inherited by the M from the ambient space Rn. In our setup, we assume that we did not know the parameterization of the manifold, and we are only given a set of point count data set S, independent and identical distributed according to a measure pi. And here we given point count data of psi n. We have the point Si to S1 to Sn. Now let me introduce the diffusion mapping. The key idea of the diffusion mapping-based PDE solver based on the asymptotic expansion. We use the notation G epsilon to represent the convolution of the kernel function H and the function U. And the function H is a exponential decay function, and with the fixed bandwidth parameter epsilon. And we can see in the second equation, we have the asymptotic expansion is equal to this one. And we can see the second term here, they involve a second order derivative in this expansion. And we can use this expansion to approximate the second order derivative in our PDE. And the L differential of this one is the differential of L is this one. And using this asymptotic expansion in the equation 2, we have the approximation of the differential operator L with using the local integration, this one, and have the error up to order epsilon. Now we have this approximation of the differential operator in the elliptic PDE, and now we approximating. We want to get the diffusion mapping discretization on the given point count data. We assume we're given a set of point count data S1 to Sn, and then the discretization of this integral is equal to the matrix W minus the matrix D. To get the matrix W, we can do the following. First, we can approximate the sampling density. Q is equal to d pi over dv, evaluate at the point Si, and the approximating sampling density Qi is equal to the sum average of the kernel function. And then we can define the coefficient for the integration on the manifold W, and each entity Wij is equal to this formula. Once we get this part, and we can divide the matrix D, and the matrix D is a diagonal matrix, and with the ith diagonal component dii is equal to the sum of the ith row of matrix W. So we have get the matrix W and D, and we can get the diffusion mapping discretization L epsilon. Now we have get the diffusion mapping discretization of a differential operator L epsilon, and we can solve get the solution by solving this linear system. And here the negative A is a diagonal matrix with the ith diagonal component is equal to the ASI. And L epsilon is our diffusion mapping discretization, and F is a vector with the ith component is equal to FSI. And then we can solve this linear system to get the solution on the given data point count, point count data. As we point out before, we can only get the solution on the given point count. So we cannot get the solution other than the given point count data. And also here the size of this matrix is of size n by n. So with the increasing number of the training data n, the matrix size will become larger. So that means solving this linear system will have the computational bottleneck to get the solution. Now let me introduce the neural networks. First is the fully connected neural network, and the formulation of fully connected neural network is equal to the composition of nonlinear function. And here we have L hidden layer, and each hidden layer HL is equal to the composition of nonlinear activation function sigma and in a linear transformation WLS plus BL. Here the NL and NL minus 1 is the width of the hidden layer, and we use the theta to be the set of all the parameters in our neural network. In supervised learning algorithm, we want to approximate the match between the given training data point Si to Yi. So that means we want to find a neural network phi as parameterized by the theta to approximate this one. And in general, we can use the empirical error defined with a mean square of this one. So the parameter of the neural network can be identified by some optimization algorithm, like we mentioned as ADAM or the stochastic gradient descent. Now let me introduce our hybrid algorithm based on the diffusion mapping and neural network. And we assume we have given data point count S, and we define a neural network of phi S parameterized by the theta, and we want to minimize this objective function. Here, L epsilon is a parameter, is the diffusion mapping discretization on the given point cloud. And phi theta is the vector, and with the ith component is the neutral network output evaluation of the neutral network on the point Si. And we want to minimize this objective function to obtain the neutral network parameterized by theta. When the A is equal to 0, we will add the regularization term of phi theta, the L2 node of this one, to guarantee the real polars of the problem. And also, when the mini-batch training is used to minimize the objective function sets, and we will select a subset of the given point cloud in each training iteration. That means we pick some rows of this differential matrix and also the corresponding entities of the function, the vector f. Now let me go to our theoretical part. And first one, we want to show that our method can give a consistent solution when we have a sufficient training sample and also have the neutral network with infinity width or infinity layers. Now we go to our theorem. We assume that the function as is strictly positive and is bounded by two positive numbers, and we give some assumption on the manifold, and then we can show that with high probability that we have this error estimation. And here the n is the number of training sample, and here the m and the L is the m is related to the width of the neutral network, and L is related to the layer of the neutral network. Actually, in this error estimation, the first three terms corresponds to the diffusion mapping discretization, and last error is related to the approximation of the neutral network. Now we move to next page. We want to show the global convergence of our method, and to establish a more general theorem for our problem, we define the empirical risk Rs with the two-layer neutral networks optimized by the gradient descent. And here the empirical risk Rs is defined as the mean square error of given the training data point S. And here A is the matrix of n by n. And in our specific application, A represents the discretized differential operator on the given data point S. And we have a neutral network is equal to this one, and here the M represents the width of the neutral network. And we consider the activation function is the root of S to the power R. So to build our global convergence theorem, we adopted the neural tangent kernel, and we consider two neural network of this form. And now we first consider we first define the kernel for the parameter AK, k from 1 to m. The kernel for the parameter A is equal to the expectation of GA over the random variable W, and W follows the normal standard normal distribution, and GA is the product of these two functions. And we can get the kernel evaluate on the training sample, it leads to the n by n grand matrix Ka. We assume that's the smallest eigenvalue of the Ka denoted by lambda s is a positive number, and also the smallest eigenvalue of AA transpose. This A is the this one is denoted as lambda A is also a positive number. And we can
yes, assume it's time. So hurry up if you might want to wrap up. 20, right? Yeah. So yeah. Anyway, you can wrap up quickly. Yeah.
Okay. So we assume theta 0 is the initialization, and we have the AK and WK initialized by the normal distribution, and we can show that when the width of the neutral network is sufficiently large, and we can show that the error, we have obtained the global convergence of the have a global convergence of the empirical loss. Now we will go through 3 numerical examples, and the first example is solving the elliptic PDE, and this one, and we have on the 2D torus embedded in the R3, and we have the true solution is equal to this one. And because we say because the A of this equation is equal to 0, so we add the penalty term here to guarantee the well-wholeness. Now we define some error here. The first one is forward error to qualify the accuracy of the diffusion mapping discretization, and inverse error to quantify the accuracy of the approximation by the diffusion mapping, and finally is the testing error. Is the error between the neutral network and the 300 Gaussian quotient points that is not in the training data set. And we can show that our solution, our result, this is our result, and then testing error can give the convergent solution, and especially when the n is equal to large, when number of training samples large, our method can still give a solution, but the diffusion mapping algorithm cannot give the solution because it involves a very large, need to solve a very large linear system. And also
So can you just give a conclusion since you're already over 5 minutes already?
Okay, sorry, and finally we will have example of with Dirichlet condition, and in conclusion we have proposed computational frameworks for solving the PDE on the manifold, and which is hybrid method based on the diffusion mapping and deep learning. Okay, this is all for my talk, and sorry for the overtime.
Okay, yeah, okay. So due to time, let's move to the next speaker.